sort of just generally talking about the differences here, we know graded potentials are small, trivial sort of fluctuations, so to speak, of the membrane potential. They're not significant. And in understanding why they're not significant, it's very important for us to speak about this negative 55 millivolts as our threshold, okay? And when I say threshold, I mean that if a graded potential is strong enough to get to this negative 55 millivolts, then it will become an action potential. But beyond that, it is not going to generate an action potential. So even if it gets to negative 54 millivolts, it'll simply fall back to that resting baseline. So again, they're small, trivial, insignificant, so to speak, and then they communicate over short distances of time. So they dissipate very quickly, right? They're not sustained the way an action potential is. On the other hand, action potentials are large, right? More meaningful changes of the membrane potential, almost a spike, if you will, of the membrane potential. They communicate over long distances of time. So think about some of the longest neurons in your body, right? The sciatic nerve goes through the entire length of your lower limb. That is the distance that an action potential must be sustained, right? So it's sustained from the axon soma, or the cell body of that neuron, all the way down to its terminal time. Okay, and so just to look at this graphically, we can see that an action potential, the graded potentials here, so these would be considered graded, did get to that negative 55 threshold. Because we did, we must fire an action potential. In this way, action potentials are what we describe as all or none. All or none, meaning that either we will fire an action potential or we will not fire an action potential. Okay, once we get to that negative 55 millivolts, we must fire an action potential. There's no half of an action potential. There's no quarter of an action potential. We must fire a full action potential, okay? So that's just sort of distinguishing both of these from each other. Let's look more closely at a graded potential. So it is initiated by some type of stimulus. So think about a stimulus on neuron X. And these stimuli can be tactile stimuli, visual stimuli, auditory olfactory stimuli, emotional stimuli. If you think about something, that can be a stimulus for action potentials and for nerves to be acting, right? So basically, varying stimuli can fire or incite these fluctuations of the membrane potential. And those would basically be congregated onto the axon hillock, and at that point, we will decipher whether or not we have substantial membrane potential change to go ahead and fire an action potential, okay? So as we said earlier, the magnitude is going to be graded, okay? We said that you can't have half of an action potential or you can't grade an action potential, but graded potentials can be graded. They can be small, they can be medium, they can be large, they can be strong, they can be weak. Okay, so graded potentials can be varied in their intensity. They are spread by electrotonic conduction, and that simply means the movement of ions. And we know this to be true. We talked about this in Unit 1. When we have that separation of charge, right, we create this battery type environment where we have this potential, this possibility, this stored energy to do work. And so the movement of these ions is how we have this being propagated or spread along the length of the axon. Also here, they're decremental. So as you can see in this sort of illustration here, we have our soma, the axon hillock, right, the neck of the axon, and then we have the remaining length of the axon. We have a stimulus on the soma, and basically we lose the strength of this stimulus as it moves further away. And this is what we mean by decremental. These potentials, these graded potentials, are not sustained in the way an action potential is because we sort of lose that intensity as it moves further away from the soma. Think about water running in a hose, right? If the hose were intact, all of that water will sort of get to its destination. If there were holes in the hose, right, we would lose the intensity, we'd eventually lose water pressure because that's escaping. And that's a similar scenario with graded potentials as they move down the axon. Okay, and just to compare them here graphically again, looking at membrane potentials versus the location of the stimulus. So this is at the stimulus, and you can see it's a stronger bump or a stronger fluctuation of the membrane potential. Whereas when you look at the axon hillock, look how much it has dissipated, right? It's significantly smaller, and that's why these are not sustained in that way. Now, the purpose of graded potentials is to determine whether or not we will fire an action potential, right? So they're not sort of unrelated to action potentials, right? They can become action potentials. So we need to consider them in that way. Again, understanding this threshold point, this threshold reference point. So we spoke about resting. This is our resting membrane potential, which is negative 70 millivolts. Negative 55 is that level or that membrane potential where depolarization is absolutely necessary. Okay, and we'll speak about the mechanism, we'll speak about the voltage gated channels that are responsible for this all or none phenomenon. But again, very important, this negative 55 millivolts, as long as our membrane potential gets to negative 55, we must fire an action potential. Very, very important. Any questions? Okay, now there are two types of changes to the membrane potential. There can be depolarizing events and there can be hyperpolarizing events. So excitatory events or events that increase or make the membrane permeability more positive, right, approaching that of sodium's equilibrium potential, will be called depolarizing or excitatory. And then our inhibitory stimuli or signals will be hyperpolarizing to the membrane potential, meaning that it's going to go more negative. Think about negative 80, think about negative 90, approaching the equilibrium potential of sodium with that negative 70 as our reference point. Okay, now potentials can sum. As I mentioned earlier, they can add. They can add to decipher whether or not we can get an action potential. Very important. They can add in time and they can add in space. In time or temporal summation, think about, again, our soma or our cell body, the axon terminal, the terminal bouton. And then if we stimulate one part of that soma repeatedly, and if those stimuli are close enough in time, they will add, right? They will add together. And again, we will determine whether or not we've gotten that negative 55 to fire an action potential. And if we do, we will fire an action potential. But the important take-home point here is we're adding stimuli in time. We're adding those graded potentials in time. Spatial summation happens at different points. So we have different stimuli on this neuron. So again, looking at our soma or our cell body, let's say we have neuron Y, we have neuron X that is synapsing onto this neuron. And so let's say neuron Y, neuron W, fires graded potential onto this neuron. Let's say neuron Y also fires a hyperpolarizing stimulus, right? So that's going to be a negative change in the membrane potential. We simply add those two stimuli together, and as you can see, they sort of cancel out. But the take-home point here is for spatial summation is that it's two different neurons, two different stimuli happening on different areas of that soma. Whereas this is going to be that same stimulus. So think about stimulus, 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 stimulus versus differing stimulus or different stimuli on the soma.